So we're going to start the next session on Spectrum. So hi, I'm Lee Champagne. I'm on the faculty here at MIT EECS, and I'm chairing this session. So we have 3 very exciting talks coming up, and I'll introduce the speakers. So first, we have Keith Winstein, and he's a PhD student of Hari. And you've heard of Mosh, which is the software that he designed, a popular remote terminal app that could work over Wi-Fi as well as compete with SSH. And what's interesting is before he came to MIT, Keith was actually a staff reporter at the Wall Street Journal. So I asked him to give me kind of an interesting anecdote each. And so Keith, go ahead.
Thank you very much. Today I'm going to talk about our new system for video conferencing that works over cellular type networks, and I'll show how we were able to beat the performance of popular incumbent systems for this kind of application. We heard a lot in the previous session about how LTE style networks are bad, that the telephone companies have this outdated mindset, and I might agree with that. But for purposes of this work, we treat sort of the network, the 3G, 4G network, as the current reality, and we say, this is what we have. Is there room for improvement on the application side, on the endpoints? Can we do better? What we found is that there's considerable room for improvement. So why are these cellular networks so challenging? What makes them different from sort of the traditional networks that the internet grew up on? One major difference about these networks is that they have highly variable link speed. So this is a recording we made of the Verizon LTE uplink. This is their state-of-the-art system. While we drove around Boston with a cell phone in a car, you can see it starts out very fast, 1,500 kilobits per second, and then it goes down to 500, then up to 1,500, then down to about 200, all in the span of 30 seconds, then up and down and up and down. And if you read the classical literature on rate control protocols and congestion control, many times there'll be a paragraph in the end, they'll say, well, we didn't analyze the case of varying link speed, or that's not a situation that we handle in this protocol. Well, this is the current reality, varying link speed, and applications and protocols that don't deal with it, we find perform poorly. That's our hypothesis, but to verify that, we actually did the experiment. We drove around Boston with every kind of cell phone you can imagine on all these different commercial networks, and we recorded the actual available throughput. Then we went back in the lab and we took real applications, Skype on Windows, Google Hangout on Windows, Apple Facetime on the Mac, and we ran them on real computers through a physical hardware box that replayed those same network traces. So it emulated the network that we had previously recorded. So let's look at the performance of just Skype on Verizon LTE, the red bolded one. So what we see here, the black line is the same black line I showed you earlier. That's the actual at the top, the capacity of this Verizon LTE uplink. And the red line here, this is what Skype is actually doing, the actual throughput that it's sending. And on the bottom, we see the delay between when Skype sends a packet and when it's available to the receiver. So this is sort of the delay between when you say hello and when the receiver hears the hello. And you can see here at the beginning, in the first 20 seconds, the delay is actually quite good. Skype is keeping the delay below 100 milliseconds the whole time. We sort of consider 100 milliseconds to be the threshold for acceptable interactivity. But it's doing that by means of an incredible conservatism about the rate that it's sent. So we have maybe a megabit per second available here, and it's sending more like 100 kilobits per second. So the video could be 10 times better. And as we look forward, we'll see Skype maintains that conservatism even as we go forward in time. Now what happens here, now we start to see a little foreshadowing of some trouble. As the black line goes down, the channel decays, Skype doesn't react to that. It doesn't accommodate the varying link speed. And there's a tiny bit of overshoot where the red line goes over the black line, and look at the consequences. It's bad. Skype, because it's sending packets faster than the network can accept them, we build up a standing queue, and we end up with a 500 millisecond delay. Now that's foreshadowing what's going to be much worse later. You can see here Skype is still wasting quality, but look at this. Now we're in real big trouble. So the network plummeted to, looks like 50 kilobits per second, which is still not that bad. You can get audio over that, no problem. But Skype kept on sending. And you can see it did slow down, but much too slowly. It needed to react much more quickly because what it built up here was a huge delay. This is like a 4-second delay. And that delay lasted for, it looks like, about 8 or 9 seconds. So because Skype, doesn't react to this kind of link variation, you end up with, from the user's perspective, an outage. For 8 seconds, he didn't get anything, or he got something that was delayed by 4 seconds, and that's really bad. Let's just look here. Let me go ahead. So if we, and there's another episode here I wanted to point out. This is actually not just a decrease in link speed, but a real outage. The network just completely, we got 0 packets for a second. So, you could say, well, it's Verizon's fault. We got 0 packets. There's not a lot the application can do. Well, that's true, but look at what happened here. The outage was for 1 second, but Skype has now compounded the problem fivefold, and it's accumulated this standing queue of packets, with a 2 or 3 second delay that lasted for 5 or 6 seconds. So yes, Verizon was gone for 1 second, but Skype has made the problem 5 times worse. All right, so if we try and summarize these results, so why is the performance so bad? Well, basically because Skype at a fundamental level and all of these existing protocols are reactive. They do what they do, and they wait to see, well, did I cause congestion? And if I get a signal of congestion, could be packet loss, could be an increasing round trip time, well, then I got to change my plan of action. The problem is that feedback arrives much too late to be able to help. If you've built up a standing queue of 1 second in each direction, then I'm sending some packets, it takes a second to get to the receiver, then that feedback takes another second to get back to me. It's 2 seconds before I learn that the round trip time has gone up. If I've been sending packets in the queue, well, now I've got 2 seconds worth of packets that are filling up the queue, and that can take a long time to drain. So this sort of reactive approach just doesn't work. The feedback comes too late, and it creates this self-inflicted queuing delay. And that is really the primary killer on these networks of interactivity. If you send too fast, you're going to build up a standing queue of packets, and then every new packet is going to have to wait in line, even if it's audio or something very high priority. Of course, if you send too slow, then you're going to waste the opportunity for better quality that you might want. So even a small overshoot can be catastrophic here. So if we had to graph Skype's performance, we would do it like this. The best would be in the upper right. The throughput here is going up, and the delay is going down as we go to the right. And Skype is here on that Verizon channel. This is looking over the whole trace, which is about 20 minutes. It gets about 1 megabit per second on average, which is not bad, but the delay that it causes, holy cow, it's like 6 seconds. And that's totally unacceptable. All right, so let's talk about our approach. Our approach is not reactive. We call it Alfalfa. And the idea here is, okay, let's figure out, in a humble manner, let's figure out what is the throughput that is available from the link. Let's try and infer that. And I'll talk about that in a second. And then, based on our uncertain estimate of the current link speed, let's try and predict what's going to happen in the future. And the farther in the future we try and predict, the less and less certain our estimate can be, because what the network is doing now, it might do in the next millisecond, but not 20 minutes from now. So we don't wait for congestion to decide how fast to send. And then we use that prediction to control the size of each coded frame. So we have an interface to the video coder. We say, okay, the next coded frame, I want it to be as high quality as possible, but our top priority is low delay. So the size of the frame is bounded by the fact that we want more than 95% probability that the frame is going to get there in its entirety in less than 100 milliseconds. So that's our control strategy. Delay is the top priority. So why do we talk about inferring the link speed from the interarrival time? Can't you just see the link speed? The problem with these networks is that they're not like the traditional internet. If you use an Ethernet, 10 megabit per second Ethernet, you send back-to-back packets, you will get packets at 10 megabits per second. Well, those concepts just don't exist in these cellular links. So this is a trace we did. This is 3 in the morning, no one in the neighborhood, no one probably else using the same cell. We flood the network. This is a Verizon LTE download, and we look at the interarrival time, just the amount of time between adjacent packets coming in. And we can see there's a very long tail distribution. It's not an even rate of packets. It's actually more like a Geiger counter of atomic decay. It's like click, 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 click. And we can see here, even though we were getting on average 1,000 packets per second, because the most common interarrival time is 1 millisecond, still we get a lot of packets that have an interarrival time of more than 10 milliseconds. In fact, we even got one pair of packets that were separated by almost 4 seconds. So that's pretty crazy. You're getting 1,000 packets per second, then you get nothing for 4 seconds. So these links really behave well, they behave differently, and so we think you need a protocol that acknowledges that it's more like a random noise process, a flicker noise process, than a steady rate.
Were you moving around at the time?
No, sorry. This is an abandoned office, 3 in the morning. I was in Vancouver. There's no one probably in the whole, practically no one within a 1-mile radius. Totally static.
Do you have any sense for why that's happening?
We have some guesses we can talk about later. Part 2, so now we've inferred the link speed. We have an uncertain estimate of it. Okay, now we're going to evolve that forward and predict, okay, I think I know what the network's doing now, but what's going to be doing in the future? Because, of course, by the time our feedback gets to the sender, it's going to be delayed. So we have a stochastic model of the network dynamics that we haven't really tuned yet, but we have one, and we use that to predict the future link speed, again, humbly, with uncertainty. So we use probability theory to do this. Here's a picture of the model we can talk about. There's a few tuning parameters, but it's quite simple. And then finally, so some of the limitations of our approach before I get to the evaluation. The stochastic model has not really been tuned, in part because this is a science project, so you can't you can't really tweak it once you've taken the data. So we had to freeze it, then we drove around, collected the data, wrote the paper. In fact, you folks this is the first time this has been presented. It hasn't been accepted yet. Our prototype uses MPEG-2 video. So most of you know this is an older scheme. It's not as efficient. So we didn't evaluate the end-to-end video performance of this application. We've only evaluated the networking performance. All right, that said, let's look at the same graph that we looked at before. The black line is going to be the network capacity. The red line is Skype. And the blue line is our protocol, Alfalfa. So we see here in the top, we're doing a lot better. We're not totally up to the black line. We're still somewhat conservative, but we're getting much higher quality video. And yet, we're still keeping the delay below 100 milliseconds. So if we look forward here, what about those bad times when Skype had problems? So here you can see Skype had a blip here. But we had a much smaller blip because we actually, in this case, we were more conservative because we sort of forecast that this was going to happen. We got cautious and we slowed down. So that because the blue line is under the black line, we didn't have the same spike in delay. Now let's look back at the real bad problem. Okay, so let's go back a bit. So here was the case where Skype really screwed up. But you can see as the black line's falling, the blue line also falls. So we stay underneath it. So we reduce our video quality gradually on a frame-by-frame basis so that we don't build up a large standing queue. And that's really how we get good interactivity, because even if we have to turn off the video or go 1 frame per minute, at least we can get the audio through with low delay. And that's a lot better than causing a 4-second delay on everything. Now here's the outage we talked about. In the outage, there really is like a second where there's no packets going through. So Skype, both Skype and Alfalfa, there's not a lot they can do. They have to have this delay. But the difference here is that we don't compound the mistake, or we don't compound the problem. Skype takes a 1-second outage and turns it into a 5-second outage. We're able to recover much more quickly. So that, I think, is a good illustration of why we do better on these metrics, because when it's inexorable that we're going to fall down, at least we can recover quickly. And when it's not, when it's just variation, we can we can produce higher quality video when it's good and worse quality video when it's worse. So this is the graph I showed you earlier, summarizing Skype's performance. And we also tested Apple's Facetime running on macOS and Google Hangout. And you can see here, Hangout actually gets less delay, but the cost is that they have much worse video quality, or at least worse video bit rate. We use that as a proxy for quality. And even so, a 3-second delay, I mean, that's really unacceptable for a video conference. We also tested TCP congestion control algorithms, which we show in green here. So you can see the default Linux TCP, which we just heard about in the last session, cubic TCP, is here. Because this doesn't really care about delay. Delay is not a signal for cubic TCP. It creates a huge delay, but it does get better throughput than the video conferencing programs. But these newer delay-triggered congestion control algorithms actually do better on this link. They get more throughput and they cause less delay, because for these algorithms, delay is a signal. And where we're actually the best on all axes. We get the least self-inflicted delay and the best video quality. And that's really the goal here, is to send the most throughput possible as long as we can keep the delay low. Now, I should confess that this Verizon LTE uplink is the example I picked where the differences are most stark, but I don't want to cherry pick here. Here's all the other links we tested. The Verizon LTE downlink, again, we're basically the best. We're the blue one. But Linux TCP actually does beat us on throughput, but at a cost of a huge delay. So this illustrates the sort of trade-off we make. We can get a lot smaller delay, but there is a small price to pay in throughput. And again, we do dramatically beat the video conferencing programs. Here's Verizon's 3G uplink. Again, we have the smaller delay, although almost everyone else actually gets better throughput than us, but at a cost of delays more than a second. Here's the 3G downlink. Same story. We actually beat all the video conferencing protocols, but the TCPs get more throughput than us, but with higher delay. Here's the AT&T LTE uplink. Similar story. We're the only one really with acceptably low delay. Verizon LTE downlink, okay, I guess we destroy everyone on that one. Actually, no, Hangout gets better delay than us, but that's because we don't think the difference between 30 milliseconds and 50 milliseconds is that big a deal, and we get much better video quality on this link. Here's the T-Mobile uplink, similar story, we're the only one with low delay. T-Mobile downlink, again, we beat everybody. So those are all the links. So to summarize, we're able to get more than twice the video quality, or at least twice the video throughput than Skype, with almost an 8-fold reduction in self-inflicted delay. With Hangout and Facetime, we get similar results, many-fold increases in throughput, well, 2-fold to 4-fold increases in throughput with many-fold improvements in delay. Compared with the TCPs, our improvements on throughput are much more modest. We're talking 10 to 30%. But again, we have huge decreases in delay. On the Linux TCP, the cubic, which doesn't really care about delay, we reduce delay by 80-fold, but that's because he doesn't care about delay. So in the future, we're going to try and improve this predictive model. It doesn't, as I said, it hasn't been tuned. We had to freeze it and then collect the data, but we think it could actually be a lot better at predicting what's going to happen. One idea would be for me to learn a lot about machine learning to do this, but a different and easier idea would be for us to hold a public contest on the internet. We haven't committed to doing this, but we're thinking we would just announce, here's 5 days of data we collected driving around in cars, and we want the whole world to see if you can do better. Can you predict these wireless networks better? And then we would, we would publish this as the stochastic model that anyone would be free to build a protocol off of, and the prize would be, you get to be a co-author with me on the next research paper. We'd like to finish implementing the video conferencing program with H.264-based video to be more efficient. This would make us competitive on an equal bitrate basis. And then we could compare the end-to-end video quality. And we'd like to generalize this. We have some ideas to generalize this, not just for interactive video conferencing, but also for stored video. So can we make a better Netflix, a better YouTube that would actually be usable on a 3G link? So to summarize, we're able to infer the link speed with uncertainty in a humble manner, predict the future link speed, again with increasing uncertainty the farther out in the future we predict it, and then we can control the transmissions to reduce the risk of a large delay. And the combination of these three techniques yields many-fold improvements in throughput and many-fold decreases in delay compared with the incumbent video conferencing programs. So I'd be happy to take any questions.
So questions? Do introduce yourself when you. Yeah.
I'm Gongmu from Intel. So how do you actually convey your predicted link speed, the information to Skype is, I assume, is Alfalfa?
Yeah, so we have a feedback message. So these evaluations were bidirectional video conferences running simultaneously in both directions. And we convey something called the packet delivery forecast. It gets sent occasionally, piggybacked on the video that has the evolution of the stochastic model, saying this is how many packets we think will be delivered over the next 200 milliseconds.
So basically, this does require the application server to
Yeah, this is a bidirectional application layer solution. So the infrastructure remains the same, but there's a sender and a receiver, and they both run our protocol. It's a bidirectional video conference.
So in the results you were showing, was one end of the conversation a fixed location, or were you mobile in both ends?
Yes, it's one. We transit one wireless link. So we transit a wireless uplink in one direction and then a wireless downlink in the other direction. But we only transit one wireless link in each direction.
Yes. So have you tried it with two?
We have not. In fact, this is not even, it's not hot off the presses because it has no press is committed to publish this yet. It was just submitted a few weeks ago. So we're eager to do more experiments.
Okay. Thank you.
Wait for the mic. Introduce yourself.
I'm Quinten from Microsoft Research Asia. And my question is that, do you think the model, a good model based on the wireless link, or is entire internet end-to-end path?
Well, the question is, do we build the model based on the wireless link or the end-to-end? I mean, the answer is that the application only sees the end-to-end network path. So the model inevitably is being trained based on the end-to-end network path. Now, where's our actual model? It's this is the problem with these things. Sorry. There's the actual model. So this is the model. It only involves one queue. So there could be some model mismatch because the model is one queue, but in reality, you could have more than one queue, and that's a penalty that we would pay.
And how complex
it does depend on that, yeah.
So actually, I thought one of the most interesting stuff with relation of your work is that really what matters is this queue that is connecting you at the ISPs to the rest of the internet. But it seems also that it is very much affected by your own self-inflicted delay. And therefore, like the end-to-end model to a large extent is this one big bottleneck that's affecting people in these cellular systems.
Yeah, I think that's exactly right.
Okay, so thank you.
Thank you.